So let's start with the webinar. It's concerning thermal conductivity measurement, which is a quite complicated topic. I will try to guide you through the jungle of this measurement methods and instruments. So my name is Hans Marx. I studied chemistry some years ago in Germany. I'm at Linzais since almost 10 years. Our application manager for thermal conductivity, Ms. Erika Hahn, unfortunately can't join in today. So if you have very precise questions concerning thermal conductivity measurement, you can contact her by email or you can contact me as well. So today's agenda is the following. I will start with a short company presentation. Show you a short overview over thermal conductivity, continue by showing measurement methods and instruments before I will go to samples and materials and how to select an instrument for thermal conductivity measurement. And I will close with a couple of examples how to select an instrument. So our company, Linzais Messgeräte, was founded more than 60 years ago by Dr. Maximilian Linzais and is now in the third generation. The actual owner is the son of Maximilian, and the two grandsons are managing directors and CEOs and head of development. So our company started to manufacture data loggers and flatbed recorders 60 years ago. This is nowadays completely out of fashion, and we focus on instruments for thermal analysis, for the measurement of thermal conductivity and characterization of thermoelectric materials. We have a couple of application labs in our factory in Germany. And we do service measurements in these labs. We have 4 companies, our headquarter in Germany. Sorry, I see that there was a comment somewhere. Okay, there is no comment, sorry, excuse me. So headquarter in Germany, we have own offices in the United States of America, and India and China, and we are represented in the entire world by a close distributor network. So our product range is very broad. Beside the instruments for measurement of thermal conductivity and thermal diffusivity for bulk materials and for thin layers, we do we manufacture differential scanning calorimeters, thermal balances, simultaneous thermal analyzers, and for the dimensional changes and mechanical properties, we manufacture dilatometers and thermomechanical analyzers. Beside this, we build instruments to characterize thermoelectric materials and semiconductors. But today's topic is thermal conductivity. So there are mainly 6 instruments I want to show to you. Those are the heat flow meters, the TIM tester, TIM standing for thermal interface material. You'll see later on what this is. LFA standing for laser and light flash analyzer. The Transient Hot Bridge, hot wire technique. And 2 instruments for the characterization of thin layers, the thin film laser flash analyzer and the thin film analyzer. So thermal conductivity is measured in the units of watt per meter and Kelvin. It starts from 0, and the highest thermal conductivity are in the range of some hundreds to 1,000 watts per meter and Kelvin. Please pay attention, this is a logarithmic scale. So lowest thermal conductivity are those from insulating materials like foams, fibers, and so on, having in general thermal conductivities much below 1 watt per meter and Kelvin. Gases have low thermal conductivities as well. Liquids in general have thermal conductivities also far below 1 watt per meter Kelvin, mercury being an exception, but mercury should perhaps better be considered as a metal, and metals have the highest thermal conductivities of all materials. Copper having a thermal conductivity of approximately 500 watt per meter Kelvin. In between are the non-metallic solids, plastics with quite low thermal conductivity, oxidic materials, ceramics in general with thermal conductivities reaching some tenths of watt per meter Kelvin. Alloys have usually slightly lower thermal conductivity than pure metals. So thermal conductivity is a quite broad range from 0 to, let's say, 1000. And thermal conductivity is also dependent on the temperature. So depending on the application material of your material, you should pay attention also on the measurement temperature. So some instruments like the heat flow meter and the thermal interface material tester have a quite restricted thermal conductivity range, temperature range, from low temperature to 100 or 300 degrees, while the hot wire method, Transient Hot Bridge, covers a broader temperature range, and the broadest temperature range is those for the light and laser flash analyzers, from very low temperature up to very high temperature. Obviously, such a broad temperature range cannot be covered by only one instrument, by only one furnace, but there are different furnaces for different temperature ranges. So let's have a look on the measurement methods. They are divided in two groups, the so-called transient or time-dependent methods and the stationary methods. In a transient method, the sample is subjected by a thermal disturbance. So you have a short energy pulse, and then this disturbance is observed as a function of time. So you have a look how this disturbance propagates through the sample. Important transient methods are the hot wire techniques and the laser flash technique. Their advantage is that the measurement time is usually very short. They cover a very broad thermal conductivity range and a broad temperature range. The drawback is that the theory is quite complicated, but this is not the user's problem, but the instruments and software manufacturer issue. And this is solved by us as a manufacturer. So stationary methods work in the way that a stable, no more time dependent temperature gradient is established through the sample. And this is achieved when the incoming energy equals the outcoming energy of the sample, and there is a temperature gradient on it. So the advantage of the important techniques are the heat flow meters, the thermal interface material testers, and also guarded hot plates. The advantage is that the data evaluation is easy. The methods are very accurate, but they need quite long measurement times, and the thermal conductivity and the temperature range are restricted. So let's have a first look on a first instrument, the so-called heat flow meters. They work according to a stationary method. So in such a setup, in such an instrument, you have a sample which is positioned between a heated plate and a cooled plate. Cooled plate and hot plate are kept at a constant temperature, while the heat flux through the material is measured by some transducers. And knowing the geometry of the sample, you can calculate by these formulas the thermal conductivity. In real life, this looks like this. You have a hot plate on top. You have a sample. and a cold plate below the sample. And between the sample and the hot side, there are some heat flux transducers. And between the sample and the cold side, there are heat flux transducers. And already said, as I already said, if the heat flux in the sample equals the heat flux out of the sample, you are in a steady state, in equilibrium, and you can measure the transferred heat and get thermal conductivity out of it. Such heat flux meters look like this. Big boxes. Behind this door, you find this assembly with a hot and a cold plate, which I already explained. Usually the samples are insulating materials like these fiber boards. The temperature range of a heat flow meter is usually quite close to room temperature because the main application is testing of insulating materials and building materials. The measurement range is quite low, usually below 0.5 watt per meter Kelvin. This covers widely the range of insulating materials. There are some measurement extensions available to cover also building materials like concrete and tiles and other materials having higher thermal conductivity than insulation materials. A typical sample size is a board or a block of 30 by 30 centimeter and a thickness of a couple of centimeters. Usually compact solids like powders are analyzed, compact solids are analyzed, but there are also adapters for powders and granules. The second hot wire technique, the second stationary method I want to show is the so-called TIM tester, thermal interface material tester. Those are materials which are used to increase a thermal contact, for example, in this case, between electronic component, which tends to heat. This should be connected to a cooler, and if you put two solids, one on top of the other, the heat transfer will be poor. And to increase this heat transfer, you can use such thermal interface materials, which can be solids, compressible solids, like in these examples, or pastes, like in the two other examples. The principle of a TIM tester is almost the same as for a heat flow meter. So you have a heat source, so a hot plate. You have a heat sink, a cold plate, and the specimen, the sample, in between the cold and the hot plate, and some thermometer to measure temperatures. This is all installed here in this assembly. And on top, you find an actuator to control the force so that you can give a certain well-defined force on your sample, which is necessary for compressible solids to have a known and reproducible compression force. Temperature range is quite close to room temperature as well, a little bit broader than for a heat flow meter. The measurement range is much broader. It goes from isolating materials up to approximately 50 watt per meter and Kelvin. And a typical sample size has to fit here between these hot and cold plates, and this can be 25 or 40 millimeter, either square or round. And the thickness usually is in a range of a couple of millimeters. So with this instrument, you can measure thermal conductivity, not only from hard and compact solids, but also from compressible materials. And you get not only thermal conductivity, but you can get also the thermal contact resistance. How this is done is explained in an American ASTM standard. So you have to prepare 3 samples out of the same material. They should have 3 different thicknesses. And then you run your measurement. And the raw data from a measurement is the so-called thermal impedance. And if you plot the thermal impedance of these three thicknesses against their thickness, you will find 3 points which are hopefully on a straight line. And from the slope of this straight line, you can calculate thermal conductivity. And the interface, the offset, is the so-called contact resistance. The example shows a Vespel material, a polymer. So those were the most common stationary method. Let's switch to a very common transient or time-dependent method, the so-called laser flash analyzer or light flash analyzer. This method is described again in a standard, and the standard says that a small thin disk specimen, a sample, is subjected to a high intensity, short duration radiant energy pulse, usually a laser pulse, but it can also be a light pulse from a xenon flash lamp. This energy pulse is absorbed on the front surface of the specimen. So on this surface, the energy is absorbed, and then the energy will travel through the sample and will come to the rear phase. And the resulting rear phase, temperature-wise, is recorded. So there is a detector, usually an infrared detector, observing the rear phase of the sample and monitoring the temperature increase during time. And from this signal, detector signal, you can get thermal conductivity. How this is done will be shown on the next slide. Let's have first a look on such an instrument. This is a laser flash analyzer. So you have a laser which is hitting a sample, which is sitting here in a furnace. So temperature can be somewhere between minus 125 and plus 2,800 degrees centigrade. So the sample is hit by this short laser pulse, and the rear phase is observed by an infrared detector giving a signal, a temperature signal over time, and this is the rear phase temperature. This goes through maximum, dividing the maximum by 2, gives a so-called half height, and the time needed to come to half height is used to calculate thermal diffusivity. This is this formula. So a constant value multiplied with a thickness squared, thickness of the sample squared, divided by this half time. This is thermal diffusivity, and in order to calculate thermal conductivity, you have to multiply thermal diffusivity by the density and the heat capacity. So there are 2 extra measurements to perform to get thermal conductivity out of a laser flash instrument. As said, the principle is a transient time-dependent method. It covers a very broad temperature range and also a very broad thermal conductivity range from poor thermal conductors to very high thermal conducting materials, so all types of materials. A typical sample size is a disk of either 10 millimeter diameter or 20.4 millimeter diameter, which corresponds to an inch. It's an American standard. This is why this diameter is often used. Such a disk should have a thickness in the range of approximately 1 to 3 millimeter, and it has to be well defined because you need the thickness, because you will square it to get thermal diffusivity. So every error you do on the thickness measurement and on the sample preparation will be squared. Samples can be round. There are adapters also for square samples. Usually the samples are compact, homogeneous solids, can be metals, ceramics, polymers, and other materials. And there are special adapters to analyze pastes, liquids, and also fine powders. The second transient method I want to show is a hot wire technique. We realized this technique in our transient hot bridge. Called THB. So as the name says, you have a wire which is heated. You have a thermometer close to this heated wire, and wire and thermometer are surrounded by the sample material to be tested. Once more, you get, this is realized in such foil sensors. In these foils are embedded hot wires, which can be heated by an electrical current, and there are thermometers. And from these sensors, which are connected to the instrument and to a computer, you get again temperature time signal. In this case, plot is done against logarithm of time. And this yields this pink curve. The green curve corresponds to the slope of this pink curve. And there is a maximum in the slope. And from this maximum, thermal conductivity can be calculated. This is done by the software. And you can get also thermal diffusivity out of this curve. So the temperature range depends on the sensor and furnace which you use. These polymer foil sensors cover a range from low temperature up to 200 or even 300 degrees. And there are ceramic sensors available going to higher temperatures. The measurement range is very broad, from isolating materials to high thermal conductors like metals. And a typical sample size are 2 blocks, because you have to embed your sensor between these 2 blocks of the sample. And the blocks have to cover at least this inner part of the sensor, which has a size of 1 by 2 centimeters. The needed thickness of the sample is in a range of a couple of millimeters, and the thickness, the required thickness depends on the thermal diffusivity of the tested material. So typical samples are these compact solids. There's a plastic, there's a metal, but you can analyze also powders, like shown here with this powder adapter. So you can fill powder in this hole, in this adapter, and insert this so-called penetration sensor in the powder. And you can analyze liquids just by dipping the sensor in a liquid. So those were the analyzers mainly intended for bulk materials. Let's have a look on the instruments intended for thin films. Those are the so-called thin film analyzer TFA and thin film laser flash analyzer. They are intended to measure really very thin films in the nanometer to micrometer range and in a moderate temperature range. So let's have a look on the thin film analyzer. It's a transient hot wire method. For those who know a little bit about the different theories, it's a 3 omega method. The thin film has to be deposited on a disposable sensor. The sensor is shown here in this picture. And the sample has to be deposited in this region. This is shown here on the picture. And then the sensor with the sample is positioned in a sensor holder, which can be heated or cooled by liquid nitrogen by these pipes. And then you can perform a measurement in the TFA analyzer, and you get thermal conductivity and also specific heat capacity. And depending on the configuration of your instrument, you can also measure electrical parameters like the Seebeck coefficient, the electric conductivity, and the Hall constant. And the second instrument dedicated for thin films is the thin film laser flash analyzer, TF-LFA. It's also a transient method, so-called time domain thermoreflectance method. In fact, it's a modified laser flash method. in a laser flash method, you use a short pulse laser to heat the sample's front surface. In a usual laser flash analyzer, this laser pulse has a length of a couple of microseconds to milliseconds. Due to the thin layer in a TF-LFA, you need a shorter energy pulse in a nanosecond range. And instead of the infrared detector in a usual LFA instrument, which is a quite slow detector, you need a faster detection technique to monitor the surface temperature. And this is done in this analyzer by reflected light. So you have a continuous light, and the intensity of this reflected light is measured. And as the reflectiveness of the surface will depend on the surface temperature, once more you can calculate out of this time temperature curve the thermal diffusivity. One important topic is that you do not do the measurement directly on the thin film, but you have to cover the thin film by a thin layer of gold, which is a reflective layer, and it serves as a kind of a thermometer because the reflectiveness as a function of time is known. So a typical sample is a sample covered with gold. So every sample you analyze is yellow. You put this sample in the sample holder in a furnace, which is here inside the TF-LFA, the thin film laser flash analyzer. So now we saw all the different methods. Let's have a look on the different materials. If you have a so-called isotropic material, life is easy. An isotropic material is a material where all properties are the same in all directions, like in this isotropic diamond structure. But some materials are anisotropic. They may have a layered structure, for example. This can be macroscopic, like in this example, a panel composed of different layers, or on a microscopic scale, like in the structure of graphite, where you find layers and the thermal conductivity in the layer will be different from the thermal conductivity perpendicular to the layer. So selecting your method, you should be aware that your material can be anisotropic, and in this case, you have to consider if your method will measure the thermal conductivity perpendicular to the layered structure, so-called through plane, or in plane, or an overall value. And the methods which you can use are different according to the direction of the measurement. Second point is the material may be inhomogeneous. For homogeneous material, there is no problem. You can analyze it with every method you like. But inhomogeneous materials have different compositions according to the space. So there may be grains of different composition and of different thermal conductivity. So your method, if it has a space resolution, a small space resolution, you will measure perhaps only thermal conductivity of one grain, while other methods measure the thermal conductivity of the whole sample. And usually you will be interested in measuring the whole sample, like in this example of a tile. So if this is the case, you have to analyze not only one sample, but to place your sensors or to cut a specimen from different places of your sample. We will see this in an example at the end of this webinar. A special example for inhomogeneous materials are porous materials. So in these cases, there will be no grains, but holes, which are usually gas-filled. And a very known example is expanded polystyrene. So polystyrene is a polymer, a compact polymer having a thermal conductivity of 0.17 watt per meter and Kelvin. But the expanded polystyrene contains holes which are gas-filled, And due to this gas-filled pores, the thermal conductivity of polystyrene is much lower than of polystyrene itself. So measuring the thermal conductivity of a porous material, you will not get the thermal conductivity of the surrounding solid, in this example, the polystyrene, but you will get the overall thermal conductivity of the solid with the gas inclusions. So there are different materials types, which I already showed briefly at the beginning. There are insulating materials like expanded polystyrene or fiber, straw, all these organic materials, often air-containing materials, which have very low thermal conductivity. And usually the temperature range you are interested in is quite close to room temperature, because most of these materials are used more or less at room temperature. An exception are fiber isolations used in furnaces, for example. Their thermal conductivity has to be known at high temperatures, even exceeding 1000 degrees centigrade. Polymers have a slightly higher thermal conductivity, but it's still a quite low thermal conductivity. And the temperature range of interest is usually below 300, often even below 200 degrees centigrade, because at higher temperature, the polymer will decompose or melt, and it has no application at high temperature. The thermal conductivity of ceramics depends strongly on their structure and composition. Porcelain, for example, has a quite low thermal conductivity of approximately 1 watt per meter Kelvin, while nitrides have very high thermal conductivities of hundreds of watts per meter Kelvin. And ceramics are often used at high temperature, so that your analysis should cover a quite broad temperature range as well. And metals have also a very high thermal conductivity from some tens to hundreds of watts per meter Kelvin, copper being the best thermal conductor beyond the metals. And often quite broad temperature range, high temperatures are needed as well. So if you select an instrument for your specific application, you have to consider some criteria. The first criteria to consider is the thermal conductivity range you are interested in. I divided them in 3 groups: a low range, a mid range from 5 to 50 watt per meter Kelvin, and a high range. And depending on the range, you have to select your instrument. The heat flow meter, you can't analyze highly conducting materials. The second point to consider is the temperature range you are interested in. Some instruments are able to measure at low temperature or close to room temperature. Others allow to measure the moderate temperature range, and others go even to very high temperature. Third criteria is the sample size and its homogeneity. So there are instruments for thin layers. There are instruments which can analyze samples in a millimeter to centimeter range, and others need very big samples in the decimeter range, like the heat flow meter. The fourth criteria would be isotropy or anisotropy of your sample and the direction of the measurement. Some instruments can analyze through the plane, others in the plane, or the same instrument, the laser flash analyzer, for example, can be used for through plane and in plane measurement, but it needs a certain adapter and sample preparation. And the Transient Hot Bridge measures an overall thermal conductivity. And last but not least, if you have to purchase an instrument, its price can be interesting as well. Laser flash analyzers being the most expensive analyzers, while the heat flow meters are the cheapest ones. So all this is summarized on the next slides. I divided them in 3 temperature range: a low and close to temperature, room temperature range, moderate, high temperature range. I divided them in three thermal conductivity ranges: a low, a mid, and a high range, and the required sample dimensions: decimeter, centimeter, micrometer range, or even sub-micrometer range. And heat flow meter is dedicated to perform measurements on isolating materials close to room temperature and on very big samples of more than 10 centimeter sample dimension. The TIM tester has a broader temperature range, goes to moderate temperature, goes to the middle thermal conductivity range, and needs samples in the centimeter to sub-centimeter range. The laser flash analyzer, being the most widely used instrument, covers the complete temperature range to very high temperatures as well, covers the complete thermal conductivity range from insulating materials to highly thermally conducting materials, and needs samples in the centimeter and sub-centimeter, even down to the micrometer range, with for certain samples and certain adapters. The Transient Hot Bridge covers the low and moderate temperature range, all thermal conductivities, and samples in the decimeter to centimeter range are needed. Last but not least, the thin film analyzer and thin film laser flash analyzers are dedicated to analyze samples in the sub-micrometer range, just the micrometer range, in a moderate to low temperature range, and the full thermal conductivity range can be analyzed. Don't worry if this was a little bit fast. You will get a recording of this webinar, and you can have a closer look once more to memorize what is shown on all these pictures. You will find also on our website some tables showing which instrument is suited for which parameters, which price, with which temperature range, and so on. So let's have a look on a couple of examples. The first example is a polymer, classical polymer application from room temperature to 100 or 150 degrees, which is often the melting point of the polymer. Sample can be prepared, let's say, in the size of approximately 10 by 10 centimeters and a thickness of 1 centimeter. So this would be such a block, for example. And thermal conductivity of a usual polymer is in the range of 0.1 to 0.3 watt per meter Kelvin. And the polymer is isotropic. So which instruments can be used? It will be too small for heat flow meter needing samples of 30 by 30 centimeters. It would fit in a laser flash analyzer, but laser flash analyzer, the method is perhaps a little bit complicated because you have to know the heat capacity and the density, and you have samples to be prepared with a well-defined thickness. This can be a bit complicated. One of the big advantages of a laser flash is the very broad temperature range, which is covered, but this is not necessary for our polymer. And last but not least, it's a quite expensive instrument. So you can run the analysis on a laser flash analyzer, but perhaps, or certainly, there is an easier method to do. And the easier method is the so-called THB. The Transient Hot Bridge has an easy sample preparation, covers the temperature range, the thermal conductivity range. Sample is big enough for the Transient Hot Bridge. Everything's perfect. Material is isotropic. Everything's perfect for a Transient Hot Bridge. You can also consider a TIM tester, but this would be a more complicated sample preparation, which would be needed. So for simple polymer, things are very simple. The Transient Hot Bridge would be the best choice. Make things a little bit more complicated. Let's go to a filled polymer. Filled polymer means you have a polymer matrix, and there are some grains included. This is often done to increase thermal conductivity of the polymer for a specific application. The application temperature would be the same, sample size the same, but the thermal conductivity will be much higher than for a non-filled polymer. It will be perhaps up to, let's say, 10 watt per meter Kelvin. And the material may be anisotropic. This material is isotropic, but if your filler has a rod-shaped structure and you do an extrusion in a certain direction, then the rods will be directed and thermal conductivity perpendicular to the sample plane will be different from the thermal conductivity in the plane. So now things are a little bit more complicated. Which instrument to choose? In this case, it would be the laser flash analyzer or the TIM tester, because these two instruments measure the thermal conductivity cross-plane, so through plane or perpendicular to the sample's plane. With a laser flash analyzer with a special sample adapter and sample preparation, you can measure also the thermal conductivity in plane. Perhaps you can also consider the transient hot bridge if you are just interested in the overall thermal conductivity, which is not dependent on the direction. And the last example for polymer, a soft polymer or a foam like shown in this picture that is compressible. Application temperature size will be the same as before. Thermal conductivity due to this air inclusions in the foam will be quite low. The material is certainly isotropic. So which analyzer should be used? In this case, the thermal conductivity will depend on the compression. So if you do a measurement of this compressed foam, there is less air in this material than in the non-compressed foam, and thermal conductivity of this compressed foam will be different from thermal conductivity of the non-compressed foam. So you have to consider that your properties of the sample will depend on the sample's compression. And the TIM tester allows to control this compression, and you will get not only thermal conductivity, but also the contact resistance. So the TIM tester could be the perfect instrument for such a compressible polymer. You can also consider the transient hot bridge. You can use it with a special accessory to control the pressure of the sample. And if very big samples of 30 by 30 centimeters are available, you can also consider the heat flow meter. So those were 3 examples of different kinds of polymers. Let's have a look on an example of a ceramic. Ceramics are often used at very high temperature. The dimensions, let's say, they are the same as for the polymers we saw before. But the thermal conductivity range is very broad. It can be 1 for porcelain, and it can be hundreds of watt per meter Kelvin for technical ceramics, like nitrides, for example. Let's consider an isotropic ceramic. The heat flow meter will not work on these materials for all of these reasons. It does not cover the temperature range, nor the sample size range, not the thermal conductivity range. The TIM tester has a limited temperature range and limited thermal conductivity range. This will not cover all of the application. And probably the sample preparation will be complicated because you need 3 thicknesses. And sometimes it's difficult to prepare thin layers of a brittle ceramic. THB will not cover the temperature range neither, so the laser flash instrument is the only instrument covering the complete temperature range and can handle the dimensions, or you can prepare samples from these block which fit to a laser flash analyzer. A second example for ceramic is a ceramic containing grains. Obviously, let's make things a little bit more complicated. So there are grains in your sample, size will be the same, thermal conductivity will be the same, but the material will be inhomogeneous. There may be grains in the millimeter range in it. There will be places where there are few grains, there are places where there are more grains. But as the laser flash analyzer is the only instrument covering the whole temperature range, perhaps you have to handle with this. And you have to prepare many samples, because depending on the place where you take your sample, this one or this one, the composition is different and the thermal conductivity is different as well. And you have to run many, many samples in order to get a mean value, to do some statistics on thermal conductivity measurement. So this can be a lot of work for sample preparation and data evaluation. Perhaps you should consider a transient hot bridge. Why? It does not cover the complete temperature range, but perhaps you can manage this. You can live with a smaller restricted temperature range, but the samples for THB are bigger, so you need less samples to get a better mean value. The measurement is very easy. Sample preparation is simpler than for a laser flash analyzer. And even if the temperature range is not covered, perhaps you can consider the THB for the other advantages. This is a picture of such an analyzer. The sensor is inserted between two blocks, and you can put it on different places of these blocks. You can prepare a couple of blocks, get a big number of thermal conductivity readings. Thermal conductivity is plotted against the incidence, so the number of measurements. In this case, 120 measurements were done with this transient hot bridge to get these distribution, and the mean value of thermal conductivity of these blocks is 1 watt per meter Kelvin. If you had to prepare samples, 120 samples for a laser flash analyzer, this would take probably days and weeks of work. For a transient hot bridge, this would take perhaps a day or so, or 2 days. So those were the examples I wanted to show. I hope that I created not more complexity than before, so that I helped you a little bit to guide you through the jungle of thermal conductivity measurement. I thank you very much for your attention up